All right, good evening. Before we get started in the content, picking up where we left off last week by talking about transformers and attention, we're just going to touch base with a really quick video about Sora, which launched this week and I think is pretty freaking rad. So I'm going to go ahead and just kind of play this, especially if you haven't seen it before. It's worthwhile taking a second. The contribution here, as far as I understand, is a text to video model that can generate a video of up to 1 minute long. And so that again, just a really cool thing. I think the video here doesn't have any audio, so let's go ahead and play it. But they show the prompt here. Oops, well, not this time. This isn't the actual prompt, but these are obviously selected, but they put in a prompt. And what's the most amazing thing about this that a lot of people have kind of observed is the consistency of the objects between frames and throughout. So this one I think was like about a 20-word prompt. They are able to, as we get kind of further into this video, we don't have to watch the whole thing, but as we get further in, you'll see that the prompts actually get really cool. The degree of precision of some of these, let me see if I can find the right one that I want to show. There we go. Here's a much longer one. So now we're kind of into the 25-30 word prompt of something that's just completely ridiculous. This is a trailer of a spaceman with a red wool knit helmet. And they talk about, they actually even like specify, if I remember correctly, that it's filmed on like a 25 millimeter on film with really vibrant colors. We can go further here, and here's a ridiculously long, oops, let me pause it here. A ridiculously long prompt of a fluffy monster, and it captures, interestingly enough, all the features of the character. Somebody's interrupting.
Yeah, well, I'm just wondering, did you optimize for video?
I did. I might not have done a good job of that. Is it not going well?
Well, it was a little jerky on my end. Is anybody else experiencing that?
Yeah, it was on my end as well, and I think his mouse has the same lag as last time.
Hey, mouse. All right. I'm on the other monitor this time, though. All right. Well, I'll try to keep my mouse
record, I'm not having any problems, so I think it has something to do with your local internet or whatever.
Okay, could be.
And I'm like way farther away than you guys.
All right. Well, this one is really cool because of the length of the prompt and the degree of precision here that goes not only into the adjectives describing the object, but also describing things like innocence and playfulness, the behavior. And this is really kind of the first time we've seen this type of attachment between text and imagery in that way. And I mean, I love soft, fluffy things, right? So like this is just completely rad all by itself. This one is interesting because of the speed. So here we have the example. Here we're asking it to draw a picture of an SUV, obviously a ton of description about the scenery, about the vehicle, and about its trajectory. But if you watch the video, what's the most impressive thing that a lot of people have kind of gravitated to is the fact that it's able to capture speed differently. The camera is moving, the field of view is moving, and all of that is happening in a manner that is pretty internally consistent. And that's been the thing that's really kind of captured people. I will jump ahead to this one just because it's cool looking. This is the one that I think everybody's kind of showing. And then let me jump to my personal favorite, which is right here. This is a drone camera above the Amalfi Coast in Italy, which is on the west coast of Italy, near Capri. What is particularly rad about this, if you've ever been to the Amalfi Coast, is it has these incredibly unique structures which are terraced buildings that they drop into the sea. Like you have a building that's like 6 stories tall and only 25 feet deep, and it just plummets into the sea. And it's kind of one of the only places in the world where this exists, and it's captured. These aren't realistic looking buildings necessarily, but the style of them is incredibly realistic. And then the other thing is that this is actually almost exactly the building that is at the top of Capri. So you can take a tram the top of the island of Capri, which is right off the Amalfi Coast, and this is literally what that looks like right there. There's a set of stairs that come up from the tram, a small building over here, and a tiny marketplace over here. And so just in terms of like the depth of reference into fact in a lot of these videos is really amazing. So I'll pause there just because I think this is a really neat, really, really, really neat thing. I mentioned kind of some of the key things that I got out of other people's reviews of this. Is there anything anyone wants to either ask about or comment in their own research or perusing of this stuff?
So I was kind of blown away by the quality. From my perspective, it seemed like it'd been a huge jump in the generated quality and consistency. I thought, if I understood correctly, it is doing this in latent space, which I thought was cool. So the diffusion through time, I think, is in latent space, and that seems really cool. And then just the speculation. I mean, how long before we're going to have a full length film that is generated just like this, And
well, considering we just went from 1 frame to what is that? 60 times 30, 18,000 frames in like, I don't know, a couple of months. So if you can expand by 18,000 in a couple months, we should be able to get to from 1 minute to 18,000 minutes in another couple months.
yeah, well, I wasn't thinking that quick, but maybe.
Yeah, I mean it's pretty freaking mind-boggling, dude.
So I think David also raised an interesting point, wasn't it, early, that it's they're characterizing it not just as video, but more as world modeling. And video just happens to be the presentation of that. But it, for the dogs to play in the snow, you got to know a lot about the world if that's the way it's happening. And if that's down in the latent space, then that's pretty impressive.
Yeah, David,
Well,
did you want to comment on that?
one thing, I don't know if you have the opportunity to test like Picalabs, Runaway, or Stable Diffusion Video. I tested the 3 of them, and it was like nice, but the consistency of background image, like an object passed in front of something, and after that it was gone, it was pretty common. So it was not realistic at all. It was just like experiments. And the video in Sora of the woman walking in the street in Tokyo, I think that is the reference video, is perfect because it's 1 minute long and it keeps consistency of everything that is happening behind the woman. So it's not generating like the images and losing the consistency of past frames. It have all the frames in its memory, and it remembers what it was behind the woman. And that's something that no any other model could do until now. And in the blog, they say it's because they have some kind of world simulator when the model understands what is happening in the world. And well, if this was here 1 minute ago, it should be here when the model, when the woman ends by pacing through this point. So it's kind of amazing. I think it's a shame that it's closed source. Like, I would like everyone to have this kind of technology, but it's also like it could create some serious deepfake. Like everyone could create deepfakes with this technology.
Yeah, so that's the OpenAI's stated reason, right? Is that they want to release this to the red team and get some feedback from some gray hacks and see what the feedback is. Just so that folks know the video that he's talking about, this is the video in Japan, and specifically what David's referring to here is you saw a woman walk behind this lady here, and in prior frame over frame, they would disappear. There we go. As they would come back out, and the ability to keep a latent model, even of things that are not within frame, is one of the unique things here. Go ahead, Ted.
Hey, so at NeurIPS there was a workshop of discussions about diffusion models, and I was flying out that day, so I didn't get to attend a lot of it, but part of it that I did attend, what the speaker was talking about is he said they were working on these, what he called 4D models, right? Because it's 3D reality plus time. So a 4D model, and they were not modeling what you see on the screen. They were modeling the whole 4D scene. And then after they've modeled that, you apply a camera position and angle, and they render the output. So really the input is like this 4D volume plus, I don't remember what camera is it 6 dimensions or whatever, 6 floats, whatever. But basically, so it sounds like that Sora is probably using a similar type model, that they're not actually trying to just render a 2D image and then continue it over time. They're rendering a scene and then they're projecting it to camera angles.
Meaning it's not model free. It's actually a 4D model of some form.
4D, so it's whatever the model is, it's progressing. It has a time element to it as well.
Yeah,
And
and
are
it
you
was
saying, Ted, that's what the person that was speaking did, or you're saying that that's what you think is in Sora?
That's what their research was, and it sounds to me, based on David's comment, that Sora took a similar approach. This is not just about extending continuity of rendered frames. It's more likely that it's a continuity of a 3D scene, and then it's a lot easier to have what you guys were talking about occlusion. Doesn't matter if you're just rendering a 3D scene. It's like occlusion will happen from a particular camera angle, but it doesn't really change the scene. Dave, were you gonna say something?
just going to add that it was NVIDIA, and apparently the actual presenter at that time slot didn't show up, so they ended up doing impromptu before the paper release presentation on that. It should probably come out. It was in the workshop? Is that right? Diffusion workshop?
It might have even been before. I don't remember. There was a workshop too.
I don't have any commentary because I don't know whether this is using only modeling the latent variables or 4D volume. In my reading about it, I didn't see anybody else kind of projecting a model, a 4D volume, and then doing camera renderings. Though the quality of images suggests that that's incredibly possible. They're so good.
Yeah, the quality that they showed at the conference was nothing like this, but the conceptual framework was there. And so like obviously, if you train it based on certain training data, like if you have a video of somebody walking down a street, okay, so now you have all the buildings for 2 blocks, you could do a completely different video, with people looking in different directions of someone walking down those same 2 blocks. But if you turn left and try to go down a side street, then all of a sudden your quality is terrible because it just doesn't have very much data, right? So by that same token, when I say it's a 4D model, that does not mean that all parts of it are equal resolution. And so, things that are slightly beyond your view or whatever very well may be much, much lower quality than the things that are like right there. Gotcha.
Cool. Well, I mean, there's more stuff coming out. There's a 4D space-time analysis in towards data science that I have not yet read. So, and Ashvin is saying that something like Unreal Engine was potentially used as a rumor. So that would certainly make things a lot easier, right? You're using kind of traditional physics engines and traditional rendering engines. So
yeah, you can use super resolution to make the final frames look mind-numbingly awesome, but the consistency is again
it's almost
the thing
impossible.
that's really
Yeah.
tricky about it. So
yeah, I mean, I think Ashvin, that's a very realistic possibility, especially if you were to like take the text analysis and for example use that to tune the rendering engine. So like being able to enforce film as a medium, for example, and the lighting, all that type of stuff.
Hey, Ted,
Be
can I
interesting.
was going to ask a question of Ted. You were talking about super resolution and consistency. Are you saying that it's kind of amazing that the consistency is handled by Sora, or are you saying that there's an issue when taking a consistent low resolution and upscaling it, maintaining the consistency during the upscale?
yeah. So I'm not sure what the either or in your question, but what I'm saying is if you generated something low resolution, you could just apply some type of super resolution technique that would make each individual frame look like amazing. You're like, wow, the freckles on that woman and the hair and the way the light reflects off, her nose. Like you can do that, but that does not mean that then you will have perfect consistency across all the frames.
On the
So
on the super resolution part.
Yeah. So
okay.
you still need enough in that lower resolution before the super resolution to make sure that afterwards you still wind up with.
Yeah.
So like the example would be if you use a low resolution image in my face and then use super resolution it, do I end up with a little bit of hair in some of those super resolution frames, or does my hair remain gone for the rest of my life?
Right.
Yeah. And you can even see things where like face generation, people will have like a little freckle here or there or whatever, right? But if you just did that a whole bunch of times, would they always have the freckles in the same spots?
Exactly.
Like that they each would look beautiful and realistic, but are they completely consistent?
Yeah. That's
Robust
true.
time.
If you think of like StyleGAN, remember they would inject at each level of super resolution, they would inject some randomness specifically to get diversity. But here we're going to need to control that injection and have some sort of deterministic output.
Yep.
That's interesting.
Yeah, or you could use something like clip where you're manipulating the output on the way out to make it consistent with the prior frame.
Yeah. Okay, fair enough. Yeah.
All right, cool. Well, with that, I love, if we want to spend more time on Sora, by the way, we can, and we can pause for today, but I do have prepared stuff for us to continue on Transformers, if that's okay, to move on.
Can I do one more side conversation on ring attention?
Oh yeah, you asked about that. Yes, please.
So I don't know how many people have heard about ring attention. It is not a different calculation. It's like flash attention. It's just a different way of ordering the steps in a basic full regular quadratic attention calculation. And the general gist of it is that if you are calculating attention on a single GPU, okay, then the amount of memory you need grows and grows as your sequence length gets longer and longer. Okay. So what they do is they chop up the calculation, and effectively, if you imagine that your memory requirement is linear in flash attention, okay, then what they do is they line up all the GPUs in order, and it's actually they connect the ends, so now it's a ring as opposed to just a line, okay? But if it's easier, just think about lining them up all in order, all right? And so let's say I'm calculating queries 1 through 100, you're calculating queries 100 through 200. The next person's calculating queries 200 through 300. Each of us needs to compare those to all the keys. Okay, so let's just say 1 through 1,000,000. Okay, if each of us only has enough memory to handle 100 keys at a time, if you have enough GPUs, okay, so if it's 1,000,000 sequence length, you need 10,000 GPUs, then each one will only hold 100 at any one time, and you do your calculation, and then basically what you say is everybody pass to your right. And so whoever started with 100, 0 to 100, they now get keys 100 to 200. And then the next iteration, they're going to get 200 to 300, 300 to 400. And so the beautiful thing about this is that at no point are you writing to your memory, your GPU memory. What you're doing instead is you're just passing to your neighbor a certain amount of information. So the way ring attention works is the length of sequence you can handle is a function of how many GPUs you have and how much memory they have individually. But primarily, it's a function. So if you have a pod of 1,000 TPUs and each of those has whatever, I don't know how many, then effectively you have 8,000 GPUs.
Or theoretically by time, right? If you're willing to wait and let one GPU process this iteratively, you basically take what used to be memory bound and you make it compute / time bound. And compute times time, actually. And so you modulate either of those.
So what surprised me is that the inter-GPU communication is fast enough to make this at all a reasonable approach. So what they do is in a transformer, you have attention layers and you have feed forward layers. Okay. So basically, while the feed forward layers are doing their very expensive matrix multiplies, all the GPUs are passing keys to each other. And apparently, if you use like NVIDIA, whatever Macaulay link, they can actually pass the keys to the other GPU faster than the GPUs can do the matrix multiplies for the feed forward layers. So in fact, the next set of keys will be waiting for you by the time you're actually ready. So it's very, very, it's whatever I'm trying to say, like your GPU utilization is as high as if you were doing a small attention that fit locally. It's not any better than that, but what's amazing is it's not any worse than that.
And by link, do you mean the CPU to GPU link, or do you mean the GPU to GPU link?
GPU to GPU, whatever, the NV link or whatever the heck they call that. And then there's the equivalent version of it for TPUs talking to each other.
This is the SLI, the board you put on top of the two.
Yeah. So basically, I mean, it has to be slower than just you writing to your GPU memory, right? There has to be some penalty for driving it off board and onto the next board, basically, right? But somehow they can do that fast enough, reasonably enough. And also, I think, the keys are not necessarily that huge in size. You're doing big matrix multiply. So it works out that basically, so I don't think because of all this, I'm trying to make money, so I'm going to be secretive about my architecture. I don't think anybody said that Gemini or Sora uses ring attention, but at least that's what I've seen people talking about. And it's a clever technique, and so you don't theoretically need to learn anything new. Just like for flash attention, you don't need to learn anything new about the way attention works. You're going to talk about attention today, Sally. It doesn't change the algorithm. It just changes which workers you have and in what order they're doing things, and whether you're writing to memory or whether you're doing this or that.
It's a pretty high class problem though, right? It's for the people that are training things that have reached the physical limit of memory, but not the physical limit of how much money they can spend on GPUs.
Yeah.
I mean, that's a pretty high.
Yeah.
It's cool, but cool.
So like okay. Anyway, yeah. So I'll finish because we got other content, but just so people know, obviously video, you're talking about a lot of frames, a lot of content, whatever. Very long sequence length if you're going to encode, 5 minutes of video into one long transformer string. And so that's what people think is that ring attention's being used.
Cool. All right. Well, thank you. And with that, I will then transition to attention. Attention, I kind of call the transformer revolution. For those of you that weren't here last week, we got all the way through 2017, 2018, and we had RNNs and LSTMs and GRUs handling text and sequential data. We had CNNs handling visual data, and we'd gone through an entire phase of what, according to oh my goodness, the history of philosophy of science. Who's the guy? The scientific revolution, the structured scientific revolutions. Anyone? Who is that guy? Thomas S. Kuhn, what he called a paradigm shift. And so we'd entered this new paradigm in 2013, 2014 of deep learning, and we had to engage in a bunch of optimizations, which Thomas Kuhn calls normal science, which is you have this new modality and you got to fix that and make it work. And then you find things that ultimately stack up and don't work. And then there's a revolution. And my argument would be that as deep learning got better, we went through all of these things and transformers became that revolution. And here's the paper. It's called Attention is All You Need. It came out of the Google Brain organization. And we were introduced to that in this meetup by a guy named Dev Vidhani. And as you can see, Dev Vidhani is a very good looking guy, and all he needs is attention. In case you're wondering, he's this guy. Oh, you weren't looking at this one, were you? Anyway, so Dev Vidhani showed up. He's here today. Dev, come on. You're not even going to respond. I'm like jabbing you directly.
I'm trying to I'm logged on from the iPad, so I have a limited view right now. So I can see the mouse move,
Okay, so you can see them. Okay, good. Well, as long as you can see the mouse moving. This is our Dev Vidhani right here. So he came up and he did a presentation on attention is all you need. I have two videos that I'd like to share with you guys on attention and transformers. The first one is a mechanism overview, and the second one goes over to the actual instruments of implementation. So it'll dig into a little bit on the on what happens inside of the blocks and what types of computational blocks are used. So this first one's about 7 minutes long, 5 seconds.
Hi, I'm Sanjana Reddy, a machine learning engineer at Google's Advanced Solutions Lab. There's a lot of excitement currently around generative AI and new advancements, including new Vertex AI features such as GenAI Studio, Model Garden, GenAI API. Our objective in this short session is to give you a solid footing on some of the underlying concepts that make all the GenAI magic possible. Today, I'm going to talk about the attention mechanism that is behind all the transformer models and which is core to the LLM models. Let's say you want to translate an English sentence, "The cat ate the mouse," to French. You could use an encoder-decoder. This is a popular model that is used to translate sentences. The encoder-decoder takes one word at a time and translates it at each time step. However, sometimes the words in the source language do not align with the words in the target language. Here's an example. Take the sentence, "Black cat ate the mouse." In this example, the first English word is black. However, in the translation, the first French word is chat, which means cat in English. So how can you train a model to focus more on the word cat instead of the word black at the first time step? To improve the translation, you can add what is called the attention mechanism to the encoder-decoder. Attention mechanism is a technique that allows the neural network to focus on specific parts of an input sequence. This is done by assigning weights to different parts of the input sequence, with the most important parts receiving the highest weights. This is what a traditional RNN-based encoder-decoder looks like. The model takes one word at a time as input, updates the hidden state, and passes it on to the next time step. In the end, only the final hidden state is passed on to the decoder. The decoder works with the final hidden state for processing and translates it to the target language. An attention model differs from the traditional sequence-to-sequence model in two ways. First, the encoder passes a lot more data to the decoder. So instead of just passing the final hidden state number 3 to the decoder, the encoder passes all the hidden states from each time step. This gives the decoder more context beyond just the final hidden state. The decoder uses all the hidden state information to translate the sentence. The second change that the attention mechanism brings is adding an extra step to the attention decoder before producing its output. Let's take a look at what these steps are. To focus only on the most relevant parts of the input, the decoder does the following. First, it looks at the set of encoder states that it has received. Each encoder hidden state is associated with a certain word in the input sentence. Second, it gives each hidden state a score. Third, it multiplies each hidden state by its softmax score as shown here, thus amplifying hidden states with the highest scores, and downsizing hidden states with low scores. If we connect all of these pieces together, we're going to see how the attention network works. Before moving on, let's define some of the notations on this slide. Alpha here represents the attention weight at each time step. H represents the hidden state of the encoder RNN at each time step. H subscript D represents the hidden state of the decoder RNN at each time step. With the attention mechanism, the inversion of the black cat translation is clearly visible in the attention diagram. An 8 translates as two words, image in French. We can see the attention network staying focused on the word 8 for 2 time steps. During the attention step, we use the encoder hidden states and the H4 vector to calculate a context vector A4 for this time step. This is the weighted sum. We then concatenate H4 and A4 into one vector. This concatenated vector is passed through a feed-forward neural network, one trained jointly with the model, to predict the next word. The output of the feed-forward neural network indicates the output word of this time step. This process continues till the end of sentence token is generated by the decoder. This is how you can use an attention mechanism to improve the performance of a traditional encoder-decoder architecture. Thank you so much for listening.
So at a high level, the idea here was to kind of introduce this concept, which steps away from the RNN model and allows us to access the information, even in its most raw forms, of the entire sentence. And that's where the concept of attention is. I'm going to try to get us to, right, there we go, to this frame. And one of the words that you hear folks like Ted referring to is a lookup or a reference. And one of the most consistent things you'll hear about attention models is that this is a softmax, which means that it's in this case 0.96, 0.02, 0.02. And so it'll sum up to 1. But the way that most people kind of think about this is that while, yes, this is a floating point number and it is a softmax, what you're kind of theoretically or abstractly trying to accomplish is to highlight. It's a lookup, essentially. And then these are somewhat more like lookup keys. And this paper this video doesn't really talk about the lookup keys. The next one that we'll get to talks about that a little bit more using a dot product, pardon me. And so we'll go into that a little bit, but this is really the primary thing, is that an RNN assumes that the most relevant thing to making the current decision in a recurrent behavior is the most recent thing. And you either have to include in that most recent thing all of history, or you have to just accept the fact that you're forgetting about stuff. It's just Every time you move forward, you throw everything away. And the primary concept of an attention-based and a transformer-based model is you should not throw those things away, and you should have a mathematical mechanism for looking back intelligently to determine which of those is the most relevant. And that is what this softmax does. It's not a hard lookup. It doesn't just look at H1 in this particular case. It looks at H1 and slightly allows H2 and H3 to be there, which, for those of us that are kind of going to get into the math here, obviously is what's necessary to learn. Because if you have it be hard, it becomes much more difficult to learn. Anybody want to jump in with comments? Otherwise, the next video is going to go into more details of the mechanisms here.
Sally, I did have a question. So this video you just went through, some of the terminology was different than I've seen around transformers on, the all you need is attention type of transformer. Is this is it casting it differently, or does it predate the?
Yeah, so actually Ted messaged me about this. It's dumbed down is the way that I would put it.
Okay.
This is the kind of more like big hand wavy video versus the next one's going to go into a lot more details about what's actually happening. And again, to Ted's earlier point, the dot product component of the lookup elements here.
Okay. I actually liked the idea that it was presenting it as hidden state. You're getting to see all the hidden state. In the other cases, it wasn't presented really as a hidden state, but in some ways that's what it is.
Yep, it's a little bit by kind of simplifying it, you do get that part of it comes out. Whereas if you jump straight into the full transformer, that part gets lost in all of the crazies.
Yep. Cool.
Yogesh.
Yeah, hi. In the example given about black cat, how does it automatically know that cat is the most important word and to assign highest weight to it?
Cool. So I'm gonna let somebody else answer that one, and I can open it up here for you guys to see it. Does anybody else want to jump in here? Otherwise, I'm gonna force either Ted or Dev to answer it. Anybody? This is the meetup. Anybody gets a chance to answer. All right, Dev and Ted, you guys fight it out. Who wants to do this one? That's my guy. That's my guy. So Devendra.
Yeah, I was going to say you go, Ted. So your question is, how does it know which one to highlight? Is that your question, Yogesh?
Yes, that is my question.
Yeah, so that's what is the process of learning, right? So essentially that highlight happens based on the transformation of the representation, the embedding that you have at that layer. So you divide that across multiple heads, and each head is essentially transforming the token or the embedding of the token to a space where over time the weights are determining what it is learning at that layer on that head. And in the process, during the learning process, it is learning, okay, this head of this layer is focusing on the representation, the mapping of this pronoun to the noun, right? If there's a reference to word it, then that head is figuring out, okay, I have to focus on the, attend to the actual noun corresponding to this term it, right? So that's what is happening in the learning process. And then when it does the dot product, it says, okay, I have to increase the focus or the value or push forward the noun from this, so that value, which is, let's say, the name of the person or the dog or whatever noun it is referring to, that will get highlighted as or get more higher value in that out of that head.
So for example, in this model here, it would learn the first word was cat, and in French, I know that the next word needs to be any adjective, and so I'm going to attend to the word that comes before the word cat in the originating sentence. So my attention will look backwards. And so as I move from this node to this node, I know that the last word was cat, and so I'm going to attend back here and look at this word instead.
Yeah. and the context length is available, or the attention heads are available to are able to look at all the entire context. So essentially during the processing, they have the whole long context or sequence, whatever length it is available to attend to.
Thank you. Thanks for explaining.
Great question. So with that, I'm going to go ahead and go into some of the mechanisms inside of this. Frequently, you're going to see things as we go forward called transformer blocks. And so this will introduce what a transformer block does and how a little bit hand wavy, but how the parts work.
Transformers are taking the natural language processing world by storm. These incredible models are breaking multiple NLP records and pushing the state of the art. They are used in many applications like machine language translation, conversational chatbots, and even to power better search engines. Transformers are the rage in deep learning nowadays, but how do they work? Why have they outperformed the previous king of sequence problems like recurrent neural networks, GRUs, and LSTMs? You've probably heard of different famous transformer models like BERT, GPT, and GPT-2. In this video, we'll focus on the one paper that started it all. Attention is all you need. To understand transformers, we first must understand the attention mechanism. To get an intuitive understanding of the attention mechanism, let's start with a fun text generation model that's capable of writing its own sci-fi novel. We'll need to prime the model with an arbitrary input, and a model will generate the rest. Okay, let's make the story interesting. As aliens entered our planet and began to colonize Earth, a certain group of extraterrestrials began to manipulate our society through their influence of a certain number of the elite of the country to keep an iron grip over the populace. By the way, I didn't just make this up. This was actually generated by OpenAI's GPT-2 transformer model. Shout out to Hugging Face for an awesome interface to play with. I'll provide a link in the description. Okay, so the model is a little dark, but what's interesting is how it works. As the model generates text word by word, it has the ability to reference or attend to words that is relevant to the generated word. How the model knows which word to attend to is all learned while training with backpropagation. RNNs are also capable of looking at previous inputs too, but the power of the attention mechanism is that it doesn't suffer from short-term memory. RNNs have a shorter window to reference from, so when the story gets longer, RNNs can't access word generated earlier in the sequence. This is still true for GRUs and LSTMs, although they do have a bigger capacity to achieve longer-term memory, therefore having a longer window to reference from. The attention mechanism, in theory, and given enough compute resources, have an infinite window to reference from, therefore being capable of using the entire context of the story while generating the text. This power was demonstrated in the paper Attention is All You Need, where the authors introduced a new novel neural network called the Transformers, which is an attention-based encoder-decoder type architecture. On a high level, the encoder maps an input sequence into an abstract continuous representation that holds all the learned information of that input. The decoder then takes that continuous representation and step by step generates a single output while also being fed the previous outputs. Let's walk through an example. The Attention is All You Need paper applied the transformer model on a neural machine translation problem. Our demonstration of the transformer model would be a conversational chatbot. The example would take in an input text, "Hi, how are you?" and generate the response, "I am fine." Let's break down the mechanics of the network step by step. The first step is feeding our input into a word embedding layer. A word embedding layer can be thought of as a lookup table to grab a learned vector representation of each word. Neural networks learn through numbers, so each word maps to a vector with continuous values to represent that word. Next step is to inject positional information into the embeddings. Because a transformer encoder has no recurrence like recurrent neural networks, we must add information about the positions into the input embeddings. This is done using positional encoding. The authors came up with a clever trick using sine and cosine functions. We won't go into the mathematical details of the positional encodings in this video, but here are the basics. For every odd time step, create a vector using the cosine function. For every even time step, create a vector using the sine function. Then add those vectors to their corresponding embedding vector. This successfully gives the network information on the positions of each vector. The sine and cosine functions were chosen in tandem because they have linear properties the model can easily learn to attend to. Now we have the encoder layer. The encoder layer's job is to map all input sequence into an abstract continuous representation that holds the learned information for that entire sequence. It contains two submodules, multi-headed attention followed by a fully connected network. There are also residual connections around each of the two submodules, followed by a layer normalization. To break this down, let's look at the multi-headed attention module. Multi-headed attention in the encoder applies a specific attention mechanism called self-attention. Self-attention allows the model to associate each individual word in the input to other words in the input. So in our example, it's possible that our model can learn to associate the word you with how and are. It's also possible that the model learns that words structured in this pattern are typically a question, so respond appropriately. To achieve self-attention, we feed the input into three distinct fully connected layers to create the query, key, and value vectors. What are these vectors exactly? I found a good explanation on Stack Exchange stating, the query, key, and value concept comes from the retrieval system. For example, when you type a query to search for some video on YouTube, the search engine will map your query against a set of keys, for example, video title, description, etc., associated with candidate videos in the database, then present you with the best match video. Let's see how this relates to self-attention. The queries and keys undergoes a dot product matrix multiplication to produce a score matrix. The score matrix determines how much focus should a word be put on other words. So each word will have a score that corresponds to other words in the time step. The higher the score, the more the focus. This is how queries are mapped to keys. Then the scores get scaled down by getting divided by the square root of the dimension of the queries and the keys. This is to allow for more stable gradients, as multiplying values can have exploding effects. Next, you take the softmax of the scaled score to get the attention weights, which gives you probability values between 0 and 1. By doing the softmax, the higher scores get heightened and the lower scores are depressed. This allows the model to be more confident on which words to attend to. Then you take the attention weights and multiply it by your value vector to get an output vector. The higher softmax scores will keep the value of the words the model learned is more important. The lower scores will drown out the irrelevant words. You feed the output vector into a linear layer to process. To make this a multi-headed attention computation, you need to split the query, key, and value into n vectors before applying self-attention. The split vectors then goes through the same self-attention process individually. Each self-attention process is called a head. Each head produces an output vector that gets concatenated into a single vector before going through the final linear layer. In theory, each head would learn something different, therefore giving the encoder model more representation power. Okay, so that's multi-headed attention. To sum it up, multi-headed attention is a module in a transformer network that computes the attention weights for the input and produces an output vector with encoded information on how each word should attend to all other words in a sequence.
I'm going to pause there for 2 seconds. It's a good opportunity to check to see if there's any more questions. I know I know there's people with varying levels of skill, and we really didn't open up by reminding people ask questions, right? Like if you understood that, dope. If you want to make a comment, cool. If you want to ask questions, that's how we all learn is from each other's questions. So if anybody's got anything, and I'll drop the link to the slides, which has the link to all the videos into the chat here. And then it's also on the Slack. Yogesh.
Hi, can you please explain the sine cosine point again, if it is possible? I didn't understand how the alternate or even helps to highlight the words.
Ed, I'm gonna look to you on that one.
I had to step away for a second. Is this positional encodings?
Yeah, it's the
Yeah.
positional. It's basically using the complementary nature of those two for the position.
Oh,
yeah, there.
So since I missed the video, I mean, just at a high level, if you're familiar, any signal can be decomposed using Fourier decomposition into a series of sines and cosines. So effectively, that tells you that sines of x2, x3, x4, kind of give you this nice spanning property, right? So they're basically using that so that if you know a particular set of sine and cosine values, that means that this thing is 7 to the left of something else, right? So you can use relative values. You can also use absolute values. That's not super detailed, but that's just the high level gist of with enough of those, you get pretty reasonable resolution to be able to do either relative or absolute location calculations.
Yeah, I think that was, Ted, something that they didn't really capture in the video. Was my understanding is you tend to have not just two, not just a sine and cosine, which gives you like one rotation, right? But you tended to have higher frequency ones as well. So lower frequency ones give you a long range. The higher frequency ones give you more resolution at short range.
Yeah, actually, if you look at the bottom right, there's an I in the formula, and what it doesn't necessarily say is there might be 30 of those for I equal 1 through 30,
Right.
and that's how you get your different signs and different cosines, and then you can, as you say, Roger, lower frequencies. There's a unique thing a far distance away for low frequency. For higher frequencies, it repeats, so you have to sort of combine the two if you wanna get sort of like precision on exactly where globally and then precision on exactly where locally.
And at a high level, and we'll go to David Sanchez as a question. At a high level, all of these things are done lots of times in parallel. You have lots of different attention heads, kind of each accomplishing learned behaviors. And so the attention heads will kind of by the nature of the training, this one will do this, and this one will do this, and this one will do this. And then when you bring them all together, it will choose at this particular stage in this particular translation task, this is the attention head that is getting me the right information. David Sanchez.
I think there is well, this is a short video, but something about before even positional encoding is the embeddings. And these embeddings are like a representation of this word or the words in the vocabulary in a latent space. Like you have every word, and every word have a space, a point in this space, but this word can change the meaning in a sentence if it's in a different position. So to represent the position of the word, because you are feeding the network with all the words in the sentences at the same time, you have to put a market in each word in the sentence. And this market is the positional encoding. It is complicated like cosine and sine because these functions actually repeat itself each amount of time. So it's very useful to mark these words and actually add them to the embeddings. For example, the embeddings can be a vector of 512, and you apply this sine function to every digit in the vector, and that way each digit of the embedding know the position of this particular word. This is a different approach as, for example, just mark one one embedding or the second or the third, because with this function you mark all of them in a way that they are not too far away and they can be easily recognized by the network. Because in other approaches, when you try to mark the position of each of the words, it can be lost if this position have a great context window. But with this positional encoding of sine and cosine, it doesn't matter the context window because sine and cosine repeat itself for a lot of time or a lot of words.
Thank you.
Cool. Thank you, David. I think one of the other important things that you brought up there, and I skipped over it, and I probably should have included just 10 seconds on it, is just that you can mathematically operate on embeddings, like that entire concept. This is a diagram that shows probably the most simple kind of way to express this, but that embeddings also frequently have relative mathematical the relative nature of embeddings, the relationship between two embedded words are not only that they're different, but they're mathematically important, depending on kind of how you do that. And that's what also enables some of the ability to operate on the words mathematically. Okay.
So the embedding has kind of superposition of multiple attributes, right? In that case, male, femaleness is superimposed on top of what was it? Rank and hierarchy.
Yeah, that's right. And all my friends in Britain don't like to refer to the royal family anymore for some reason, but we can let that go. You can watch that on Netflix. All right, any other questions? Cool. Otherwise, we're right on track to finish Transformers today, and that's it. Ted mentioned in the chat here, there are lots of different ways to do settings, and this is just one of them. So I'm going to go ahead and we'll start again here, and I think we'll get to the end of Transformers and attention today, which is cool. Perfectly on point.
The multi-headed attention output vector.
Sorry, I went too far.
Next step, the multi-headed attention output vector is added to the original input. This is called a residual connection. The output of the residual connection goes through a layer normalization. The normalized residual output gets fed into a pointwise feed-forward network for further processing. The pointwise feed-forward network are a couple of linear layers with a ReLU activation in between. The output of that is again added to the input of the pointwise feed-forward network and further normalized. The residual connections helps the network train by allowing gradients to flow through the networks directly. The layer normalizations are used to stabilize the network, which results in substantially reducing the training time necessary, and the pointwise feed-forward layer are used to further process the attention output, potentially giving it a richer representation. And that wraps up the encoder layer. All of these operations is for the purpose of encoding the input to a continuous representation with attention information. This will help the decoder focus on the appropriate words in the input during the decoding process. You can stack the encoder n times to further encode the information, where each layer has the opportunity to learn different attention representations, therefore potentially boosting the predictive power of the transformer network. Now we move on to the decoder. The decoder's job is to generate text sequences. The decoder has similar sublayers as the encoder. It has two multi-headed attention layers, a pointwise feed-forward layer, with residual connections and layer normalization after each sublayer. These sublayers behave similarly to layers in the encoder, but each multi-headed attention layer has a different job. It's capped off with a linear layer that acts like a classifier and a softmax to get the word probabilities. The decoder is auto-regressive. It takes in the list of previous outputs as inputs, as well as the encoder outputs that contains the attention information from the input. The decoder stops decoding when it generates an N token as an output. Let's walk through the decoding steps. The input goes through an embedding layer and a positional encoding layer to get positional embeddings. The positional embeddings gets fed into the first multi-headed attention layer, which computes the attention score for the decoder's input. This multi-headed attention layer operates slightly different. Since the decoder is auto-regressive and generates the sequence word by word, you need to prevent it from conditioning to future tokens. For example, When computing attention scores on the word am, you should not have access to the word fine, because that word is a future word that was generated after. The word am should only have access to itself and the words before it. This is true for all other words where they can only attend to previous words. We need a method to prevent computing attention scores for future words. This method is called masking. To prevent the decoder from looking at future tokens, you apply a look-ahead mask. The mask is added before calculating the softmax and after scaling the scores. Let's take a look at how this works. The mask is a matrix that's the same size as the attention scores filled with values of zeros and negative infinities. When you add the mask to the scaled attention scores, you get a matrix of scores with the top right triangle filled with negative infinities. The reason for this is once you take the softmax of the mask scores, the negative infinities get zeroed out, leaving a zero attention score for future tokens. As you can see, the attention scores for am have values for itself and all other words before it, but 0 for the word fine. This essentially tells the model to put no focus on those words. This masking is the only difference on how the attention scores are calculated in the first multi-headed attention layer. This layer still have multiple heads that the masks are being applied to before getting concatenated and fed through a linear layer for further processing. The output of the first multi-headed attention is a mask output vector with information on how the model should attend on the decoder's inputs. Now on to the second multi-headed attention layer. For this layer, the encoder's output are the queries and the keys, and the first multi-headed attention layer outputs are the values. This process matches the encoder's input to the decoder's input, allowing the decoder to decide which encoder input is relevant to put focus on. The output of the second multi-headed attention goes through a pointwise feed-forward layer for further processing. The output of the final pointwise feed-forward layer goes through a final linear layer that acts as a classifier. The classifier is as big as the number of classes you have. For example, if you have 10,000 classes for 10,000 words, the output of that classifier will be of size 10,000. The output of the classifier then gets fed into a softmax layer. The softmax layer produces probability scores between 0 and 1 for each class. We take the index of the highest probability score and that equals our predicted word. The decoder then takes the output and adds it to the list of decoder inputs and continue decoding again until the end token is predicted. For our case, the highest probability prediction is the final class which is assigned to the end token. This is how the decoder generates the output. The decoder can be stacked n layers high, each layer taking in inputs from the encoder and the layers before it. By stacking the layers, the model can learn to extract and focus on different combinations of attention from its attention heads, potentially boosting its predictive power. And that's it. That's the mechanics of the transformers. Transformers leverage the power of the attention mechanism to make better predictions. Recurrent neural networks try to achieve similar things, but because they suffer from short-term memory, transformers are usually better, especially if you want to encode or generate longer sequences. Because of the transformer architecture, the natural language processing industry can now achieve unprecedented results.
All right, I will leave his grand comments to himself there, and we can move on. We did get a bunch of questions in the chat for those of you that aren't paying attention to the chat about whether there's a way to get caught up on some of the fundamentals. There's some good recommendations there. At a high level, join the Slack channel, and what we'll do is we'll make sure we've got a really strong group of people that'll participate, and we'll put together a list of probably 10, 20, 30, 40 videos there that you can go through and catch up. Yogesh, you had a question?
For asking questions on Slack, is there like certain rules, or like you should only ask after this level, or like you should be familiar with linear algebra, something like that?
No. You can ask any question you want anytime. That's again, I will continue to encourage that. There are 2 rules. No porn. And I know that's the only rule, I think, actually. Yep, there you go. Okay.
Thank you.
And you think I'm joking, but I'm not. So if you watch some of our videos, you will notice that we get Zoom bombed every once in a while. And yeah, so
Requires
really
editing.
Yeah. I wish I were totally joking. All right, cool. I'm gonna actually keep us going, which is awesome, and I'll move us into generative because I have a quick, again, kind of high level description of the early days of generative models. So as we heard in the transformers, one of the primary tasks for text-based models is they talked about question answer. They talked about translation models, and they also talked about generative models. And what it turns out that's really interesting about generative or predictive models, can I predict what the next word is going to be in this sentence and just create a bunch of text, is that those can be trained using self-supervised data or unsupervised data. And that massively increases the ability to take all the data on the internet and say, just run, right? And you don't have to label it. You don't have to have, oh, is this an accurate translation of French to English? You can literally just run. And then once you have the language model, the ability to kind of climb and use those latent language models to then do things like translation, to do things like better embeddings or identify the correct embedding layers and methods, then you get that as a building block to build these more complex models. In the context of transitioning that, now I'm gonna kind of use transformers, that video, to put a wrap on text, and then start transitioning us into image and video in the generative form, and then we'll see those two worlds, obviously, right? Like we just showed Sora, those two worlds converge. And so we're gonna separate again, and then we'll converge next week. So I'm gonna show one really quick video that I really liked. Because of time and because I think the rest of the video is not that interesting, I'm gonna start this one at about 2 minutes and 30 seconds, it looks like.
Or, as I've already mentioned, diffusion models, where we're transforming Gaussian noise to newly generated images. Or why not try cascaded diffusion, where we simply strap 3 Unets in a row for even higher resolution generative creations.
Unet rule.
As you may have noticed, all of these tasks take an image as input and produce a new image. For example, in segmentation, we are trying to learn a mapping from the pixels of an image into the pixels of the segmentation mask. If we have ground truth data, such as hand-labeled segmentation masks, then we can train a machine learning model, such as the Unet, to predict these masks and hopefully generalize to new unseen images. For example, with a set of input images and hand-annotated segmentation masks, we could train a Unet model. By passing in our images to our model, we can produce an initial guess at the ground truth mask. Initially, our guess won't be very good. However, we can still use it to compare against our ground truth label. This comparison gives us an error we can use to adjust our model's parameters, meaning that the next time we pass in an image, we'll have a slightly better prediction. So why is this model so effective when working with high-resolution inputs and outputs? Well, the Unet model consists of an encoder followed by a decoder. The encoder is responsible for extracting features from the input image.
Again, I'm just going to pause here for 2 seconds. As you saw in the transformer video, we're seeing these kind of encoder-decoder approaches. This video is really to kind of hammer into there's a type of network called a GAN that this is going to kind of feed us into and describe why this architecture that's called a Unet has become so popular in the generative types of artificial intelligence.
Whilst the decoder is responsible for upsampling intermediate features and producing the final output. The funky thing about Unets is that the encoder and the decoder are symmetrical and they're connected by paths. This design gives the model its namesake, the U. The Unet is known as a convolutional neural network with an encoder-decoder type architecture. This means we process images, such as this man on a bike, and attempt to extract useful features, such as recognizing these 2 bike wheels. Once we have a rough idea that this area probably contains a bike, we then decode these features back to their former resolution in an attempt to get a pixel-perfect representation of where the bike is in the original image. have another look at the architecture and see if it makes a bit more sense. Let's have a closer look at the encoder, the decoder, and the connections in between them, based upon the original paper. Features are passed through an encoder consisting of repeated convolutional layers and max pooling layers that extract intermediate features. These extracted features are then upsampled by a corresponding decoder, where saved copies of the encoder's features are concatenated onto the decoder's features via connecting paths. The final layer produces the output. For example, this could be a segmentation mask. You can then simply calculate your loss with respect to a ground truth mask and backpropagate the gradients through the network to improve your model's predictions. Let's recover what we just learned and go over each of the model components in a little more detail. Let's check out our first protagonist. The encoder is made up of a series of repeated 3x3 convolutional layers at each of the stages. After each convolutional layer, the ReLU activation function is applied element-wise to each of the features. In between the stages, a 2x2 max pooling operation downsamples the features. This is a stride of 2 and is the equivalent to picking the largest value in a non-overlapping window rolled across the image. This of course reduces the spatial dimensions of the features, and to compensate for this, the channels are doubled after each downsampling operation. Now let's have a look at the next part of the network, the decoder. The decoder, in many ways, is the reverse of the encoder. It is also made up of a series of 3x3 convolutional layers, each of which is followed by the ReLU activation function. Instead of downsampling with max pooling, the decoder upsamples the current set of features and then applies a 2x2 convolutional layer that halves the number of channels. The upsampling operation is used to restore the spatial resolution of the features that were lost during the encoding phase. There are two types of connections between the encoder and the decoder. These are known as the bottleneck and the connecting paths. First, let's look at the connecting paths. The connecting paths are simple. They simply take a copy of the features from the symmetrical part of the encoder and concatenate them onto their opposing stage in the decoder. This simply means place alongside the decoder's features, meaning subsequent convolutional layers can operate over both the decoder's and the encoder's features. The intuition here is that the decoded features might include more semantic information, such as this area is a bike, whereas the encoded features contain more spatial information, such as these are the pixels where the object is.
I'm going to pause there just because I think this is this is probably the key I think the key concept of a Unet right here is that in a typical encoder decoder, you're challenged by the problem of a limited amount of information that goes through that bottleneck. You're essentially compressing and trying to come up with the smallest possible completely covered representation of the original information from which the the decoder can then regenerate the original data. And what we've seen is that in general that process is lossy. And so in the context of CNNs, there was this concept of a residual layer where you pass the original data on and you're able to refer back. It's different than a memory. It's actually going back to the original data. In this case, it's using the latent space of that, but it's going back to the original data. And so it looks like Randy just asked a question about upsampling being inaccurate. That's exactly right. That if I just know a bike is in this region, it's going to be almost impossible for me to just know, even if it's a yellow Trek bike, like, or whatever, right, to get a pixel perfect output. But if I have the latent space of the original encoding process, I have a much better probability of being able to fully capture that, as well as my loss at the end will be more information. It'll contain more information for me to train my network so that I'm capturing the right features in the bottleneck. And then as I'm reconstructing it in the upsampling, doing that accurately. And Ted, Roger, Dev, anybody want to add anything to that?
No, I think you hit the nail on the head brilliantly, that there's this pattern that you want to extract the core concepts. This is a German Shepherd. That's great. Like that's very specific. Like I'm looking at a picture of a German Shepherd, but if you do that, you've now lost. Well, is it standing indoors or is it standing on grass? Is it facing the left? Is it facing to the right? Is it old or is it young? So compression, of some kind of bottleneck, latent, whatever, gets you these really great meta concepts, but you need something else, and that's where all of these different models for different data types have that in common, that you somehow need the big picture, but you also need to say, I don't want to lose all the details when I go about that.
And so as we get into diffusion models, the ability to kind of tweak as you're upsampling, that becomes really, really important. And again, as we're trying to make that upsampling match text, for example, every step in this process becomes a great opportunity to say, oh, nope, not quite this way, go this way. Yes, that's a German Shepherd, but it has a pink nose, or whatever, right? And so you're getting all these opportunities to kind of gently manipulate things towards the correct outcome. All right, with that, I'll keep going, and then I think we've only got a minute or two left on this one.
When you combine both the decoded and the encoded features together, you can see how you can get pixel-perfect segmentation. Now let's have a look at the bottleneck, the bridge between the intermediary features of the network. This is where the encoder switches into the decoder. Firstly, we downsample the features, then we pass them through the recognizable convolutional layers, before finally upsampling them again to their previous resolution. Let's run through an example. First, we pass our input image through the encoder, passing them through the 3x3 convolutional layers and ReLU functions. At each stage, we downsample them with a 2x2 max pooling layer and double the channels before passing them through the convolutional layers for this stage. This repeats all the way down to the bottleneck. At the bottleneck, we downsample, pass the features through the convolutional layers, and then upsample the features to get back to the corresponding resolution before the bottleneck. We now pass the features up the decoder, upsampling the features as we go, and at each stage we also concatenate the features via the connecting paths. This pattern of upsampling, passing through convolutional layers, and concatenating the features repeats all the way to the final output layer. And there you have it. That's the overview of the Unet machine learning model architecture. As we've seen, the Unet architecture is pretty simple when you break it down into its components. It uses ideas similar to that of residual networks, where we only need to learn the difference between the input and output pixels. Since the connecting paths pass in copies of the input features, it makes it easier to gain pixel-perfect accuracy for tasks such as segmentation. The Unet can have impressive performance even on small datasets. By applying data augmentation techniques such as flipping, rotating, color altering, and scaling. These techniques help create new training examples from existing ones and make the model robust to visual transformations. A bike is still a bike, even if I rotate it 30 degrees or flip it. In recent work, researchers have found great success by training conditional Unets. For example, in the diffusion model framework, we can train a Unet that has been conditioned on both time and conditioning text. This helps us guide a generative process to convert Gaussian noise into any image under the sun given enough training data. The Unet model is a powerful tool in computer vision. Its unique architecture.
All right, he's about to wax poetic. I don't think we need to listen to that part. But again, I think that we've done a good job of kind of getting ourselves to this generative, and my hope would be next week we can do a real quick introduction to diffusion and talk about SDXL. If we do want to spend more time kind of getting our way there and taking it a little more stepwise, happy to do that. And given everything going on real time, I think it would, to Roger, to your point, it'd be pretty cool next week if we spent some time talking about new stuff too. Just because, this was really awesome. The SDXL Turbo was like crazy awesome 2 months ago. And now watching it just, I felt like so underwhelmed coming to present this with Sora coming out this week. I was like, oh, cool. But yeah, any questions before we wrap up tonight? Happy to answer any more questions. Or again, I think the idea of putting together some beginner's guides on Slack is a great one. Great suggestion.
I think there was a request in the chat that next week you do technology behind the Commodore 64.
Yeah, so I'm a retro hardware dude, and so I can do realistic audio and three-dimensional graphics on Commodore 64. The presentation will be about 75 years long, and it will render one image. Yeah, wow.
No, just kidding. But I mean, this is great, and I still want to hear the Stable Diffusion XL Turbo stuff, because I think it's still very interesting to see the techniques. Maybe there will be some supercharged version of it that's way better than this version, but the concepts sound like, you know, they'll likely get reused at some point or whatever. So I'm still very interested in that. Even though, yes,
for
like
example,
2 months is an eternity.
I mean, if Sora is really just a rendering engine sitting on top of a 4D space, then I think the concepts that are explored in Sora or not in Sora, in SDXL Turbo will still be really important, because the combination of a GAN in terms of the visual acuity and consistency with the amazing kind of power of a diffusion model, that combination and doing it quickly is still really powerful. So again, any questions, I'm happy to answer those. Otherwise, we can wrap for the week. All right.
I wanted to add
Roger.
I wanted to add a comment around the questions, and just to make everybody feel comfortable with asking even the most basic questions on Slack. I think all of us, one of the best ways to learn things is to teach things. So in responding to those basic questions, it really helps. Just like this review, we've gone back through history. We've all seen many of these before, but it's useful. It's helpful to see it again. So yeah, so feel free to ask even the most basic question. And then along the same lines, one of the best ways to learn something is to teach it. And so our group really actively invites people to come in and present topics. You don't have to be an expert in it. It shouldn't be an onerous task to prepare for it. You just need to be able to kind of lead the discussion. That's a great way for you to learn. It's good for everybody else to contribute. And I think we also really enjoy the diversity that it brings into the group, different topics. It just makes it much more interesting. So both of those invitations.
Yeah, I mean, for example, like I was kind of joking about Dev earlier. We were 100% for like 2.5 years on video, and Dev came in and said, I really want to talk about text a little bit. And it was out of left field, and it was one of the most transformative presentations we've had in this group. And so I want to point it at that specific example, because that's how we learn, right? I mean, this isn't a group of professors. This is a group of people that enjoy stuff, and none of us know this stuff well enough to say, you're wrong and you're right. Like this is about exploring and finding the right answers.
And I didn't know that now you can find so many different images with my name up there.
Even Dev learned something this week.
For what it's worth, I think you are the most handsome of all those images.
Oh. Now that we got that on tape, I'm going to stop the recording.
Yeah, let's stop the recording.